All right, the talk basically consists of 3 parts. The first part deals with comparing 2 binaries by using their structural properties, using the graphs within the binaries instead of using the instructions. And that is quite beneficial for doing, first of all, diffing of binaries. If somebody releases a security update and you want to know what the bug was, what are they changing in the new version of the binary, you can use this to find out what they changed. Secondly, it's useful if you have a version of the binary for which you have names for the functions, or which you have disassembled already, and you would like those names to be used in another version of the same executable. You can use the graphs later on to port that information from one binary to the next one. This is quite useful if you have, for example, an old version of Checkpoint Firewall where they left the symbols in 2 or 3 years ago, and you would like to use those symbols in your versions as well, because it does simplify the process of looking through the binary a lot. The second part will be about navigating through unknown binaries. Binaries are not exactly the nicest place to be in terms of you don't have any names, you don't really know where you are, where you're going. And I'll speak a little about restructuring the flow graphs of a binary in order to actually understand what's going on. I'll speak a little bit about hooking the graphs into a debugger and painting colors into the graph to visualize things better. And then I'll speak a little bit about what properties in the graph you might use for focusing what code you should be auditing first when you're looking for bugs. And at the very end, I'll speak a little bit about, or it's not really speaking about, I'll show some interprocedural data flow analysis, which I've been doing. And that's basically using a graph to answer questions like, which APIs exported from MSASN1 DLL eventually pass an argument to a memory allocator and do an addition beforehand so we can do fun things. All right, so let's start about binary diffing. The security patch analysis process became really interesting with LSD's decom bug publication because we had the situation that everybody knew there's a bug, but the details were all kept quiet. So everybody wanted to start finding out what the bug actually was. Now, in the general case, very few organizations install patches really quickly. Actually, in Germany, there's a really weird law where financial institutions are disallowed from installing patches on critical systems without testing them for at least a week, which is a fantastic legislation. Love your law. Well, in the general case, the agreement is that not publishing any information concerning the vulnerability when you release the patch buys the customer time to install patches. This is the reason why Microsoft wants all the security people that actually give them information about a bug to keep quiet about it until they've had time to release the patch and install the patch. And Microsoft thinks they're buying time for their customers. This comes from the fact that there's an asymmetry between the problem of reverse engineering a program and just recompiling it. Making the change and recompiling the executable is really easy, whereas reverse engineering it is really time consuming. The general assumption is that the reverse engineer has to reanalyze the entire application and then start comparing the different functions in order to find out what changed. Both software vendors and high-level language virus authors try to exploit this asymmetry. High-level language virus authors want to buy time from having antivirus signatures and so on and having the antivirus team really know what's going on. And software vendors just want to buy time for their customers. Now, diffing executables on an instruction level is really difficult. A very small change in the source can trigger significant changes in the executable. Adding a structure member will change all the immediate offsets which deal with that structure. If you have a structure of, I don't know, 16 members, and you add a member in front of it, all access to that structure in the binary will change, like the immediate values for addressing the members of the structure will change. Adding a few lines of code can have drastically different register assignments as a result because the compiler will always use which register is free when it's compiling. And as such, if you just change a few things, it can lead to being completely different registers used throughout the entire function. Another problem is that many compilers these days, or many linkers, try to arrange the basic blocks of every function in an optimal way, having everything aligned, having everything in place. So growing one of those basic blocks can trigger a change throughout the entire binary where all basic blocks are rearranged. And if you're dealing with Microsoft executables, they have a weird, aggressive runtime linker optimizing thing. They call it profiling-based linking optimization or whatever. It's going to be part of Visual Studio 2003 or 4. I don't know, like the next version of Visual Studio is supposed to have it. And Microsoft has been using this for a few years, where they basically create profiling information about every basic block in the application, and then they know all the regular trodden paths. So if you have a function or you have an application which has error handlers, I mean, a significant part of any application is error handlers. Those will not be executed all that often. So Microsoft takes all the basic blocks which are not executed often and puts them on a different page than those that are executed often. This leads to better performance with, well, due to the prefetching stuff. It definitely leads to a lot better paging behavior of applications because the operating system can page out lots of code pages which are not used all the time. Now, the overwhelming majority of the instruction changes in a binary are irrelevant for us as a security analyst because, well, we don't care about immediate changing for structure access, and we don't care all that much about a different register being assigned. We care about bugs and we care about logic changes. So we have to start making a trade-off. Can we risk more, well, can we reduce the number of false positives by risking that we have a false negative at times? Now, the main thing that I'm doing is, or what makes my approach different from many others is, you regard a binary as a graph of graphs, meaning we're looking, well, first of all, we're looking only for changes in program logic. We're not looking for a constant change or whatever. So we're looking at the program as a graph of graphs, meaning you have one large graph which contains all the relations the function have to each other. Function A calls function B calls function C, function A can also call function C. That's the large graph. Now every single function in itself is a graph as well, which is the flow graph of the function, which has all the basic blocks and the if blocks and so on. So the program logic is more or less encoded in these two graphs. If you add a single if inside of a function, you'll trigger a change in its flow graph. If you add or change a function call from string copy to strn copy, you will change the call graph. So the program logic is more or less encoded in these other graphs. Now, what I'm doing is I'm trying to find the changes by comparing the flow graphs only. And this actually should detect all logic changes. As soon as somebody adds an if, he will be changing a flow graph, and I should see it. So in theory, this comparison should be false positive free. I should only get changes that actually change the logic of a program. Because, well, if somebody just, or if the compiler just does rearrangements, he can't change the logic of the flow graph too much. So, well, there should not be a false positive. In reality, there are a few false positives occasionally, because, well, some modern compilers inline entire functions if they feel like it, and so on. So false positives can occur, but there are significantly, like, there's very few of them. The big disadvantage of using the graphs only is that the comparison will not be false negative free. Meaning if somebody just changes a buffer size or, well, a constant, I will not see it because I'm never looking at any immediates at all. I'm just looking at the graphs. So then again, I mean, the usual way that security vulnerabilities are fixed is not by somebody enlarging a buffer. If there's insufficient size checking, you add an extra check normally, and you don't start enlarging buffers. And I have some ideas about how to go about not missing as many problems as I'm missing now, or not missing stuff when people are enlarging buffers. Now, the general question is, how can you compare two graphs of graphs? The problem is that if you have, well, showing that two undirected graphs are isomorphic, math speak for equal, is really damn expensive. So, well, fortunately for us, we don't have an undirected graph, and we can do a lot of other things. First of all, we have a directed graph. The call graph is directed. All program execution is always directed in a way. And the other thing is, showing that two graphs are the same gets a lot cheaper if you have a large number or a number of fixed points, meaning two nodes in, like a node in a graph each, like one node in the left graph, one node in the right graph, and you know those are definitely the same. That allows you to try to show the graph isomorphism in a lot cheaper manner than usually. So when you're analyzing programs, we have the entry points of the executable, meaning, okay, function main is called, you can start up. And you have certain function names which have been exported because of importing DLLs or whatever. So we do have a bunch of fixed points to start with. And unfortunately, this is usually not enough to just start with these. So having more would be desirable. So a horrible mathematician, which means I'm not coming up with a sound way of finding more fixed points. I came up with a relatively stupid heuristic to find these things, which seems to work fairly decently in practice. You generate a signature for every function consisting of its number of basic blocks, its number of edges, and the number of functions called from this function. And before you generate the signature, you have to do some restructuring if the compiler has chopped off some things, but we won't go into this too much. So the signature in a function like this here would consist of 5 for 5 nodes, 6 for 6 links, and 6 for 6 subfunction graphs. So we get a tuple of 3 small integers, or integers, describing the graph. And then we're left with, like, when we compare to executables, we have these 2 big sets of tuples. And now we try to find tuples that are unique in each of these sets. So for example, the tuple 39, 66, 33 is unique in both executables. So we assume that this is a fixed point. These 2 are the same. Then we remove them from the set. And we continue with this. 18, 32, 23 is unique, until we run out of unique matches. And once we're left with matches that are not unique anymore, we use the information from the fixed points to match other ones which have collisions. Like, you will get a lot of collisions, especially for small functions, meaning if you're counting nodes and links, for example, if you have a function consisting of 2 nodes, or 3 nodes, or 4, there's not that many ways you can arrange those 4 nodes with the different branches. So the smaller the function is, the more likely it is for you to have a collision. Now, in order to resolve these collisions, we use the call graph. If we know that the 12, 19, 7 node is a fixed point, like we have a fixed point for the 12, 19, 7 node, then we look at the subsets in the 2 sets of the functions that are called from the fixed point. So we iterate over all fixed points and improve the mapping by looking at the children called from a function, and then see whether, if you only look at the small set, these match, like there's a unique match. This, well, obviously, if the sets you're comparing are smaller, then the probability of you having a collision is a lot lower. So in our case here, we have a fixed point for the 12, 19, 7 node, and we look at the children, like the children of this node in the graph. And if you look at the children, it's clear that the 2 to 1 node is unique in both sets of children, so we can match the 2 to 1. And now, as we have the 1 2 to 1 matched, we have resolved the collision and we can match the other 2 to 1 because all of a sudden it's unique. All right, so let's get into a small example. All right. Here we go. So here we have Microsoft's H323 ASN1.dll, which, well, Microsoft published a patch for ISA Server at the beginning of this year, I think, or at some point in the past. And they were patching a vulnerability in H323, which some people from the British government had found. And nobody really published what the problem was. And while doing the binary diff, we get this window here which tells us which function is associated with which other function. Like the 42ED12 function in one binary is the same as the 42EBFA function in the other binary. And on the left side, you see over here whether the function did change or not. And we're left with a very small number of changes here. And then we look at the 2 graphs of the functions and try to find out what the changes between them was. So we can see that this function looks relatively similar. And I currently am working on a heuristic that tries to highlight what actually changed in the graph, which is a bit of a hard problem. So we see the old function here does a call to ASN1 per deck U32 value, read an attacker supplied 32-bit value. All right. Same thing in the other one. And all of a sudden, the other one has a change here. This block is not the same as this block because there's some comparison of the decoded value to OE hex. And if that decoded value is larger than OE hex, then EAX is zeroed out, and the function returns. So what's happening here is they are introducing a range check on a variable taken from a packet. And if we look down here, the graph has loops highlighted, which means the green thing is an entry point to a loop, and the blue thing is an exit point to a loop. You see that they're decoding 16-bit values into a buffer. And in the old version, they were just taking these 16-bit values from the packets or from the ASN1 stream, and they were not checking the number of 16-bit things they would be decoding. So you tell, oh, please decode me 20 megabytes of 16-bit bits which I'm supplying, so you can smash the buffer with any data you want to. So this was one of the things they fixed. That was interesting, but not quite as interesting as in the next one. Let's look at the next one. What do we have here? Again, we have the ASN1 PER decode unsigned 32 value, which we have over here as well in the old graph. Down here. So they're decoding, then they call deck alignment, and then the old version, they just go straight to deck 0 table char string no alloc without checking the value from the packet. And in the new version, they're checking whether the value from the packet is smaller than 81 hex before they jump over here to ASN1 PER deck table char string no alloc. So something is fishy with this ASN1 PER deck 0 table char string no alloc, because obviously if you don't check your arguments going into it, something is going to blow up. And if you actually look at the function, you have a nice integer wrap and heap corruption afterwards. So they introduced a lot of checks in ISA server to prevent a bug in MSASN1, like the integer wrap itself, the function they're calling is in MSASN1, to surface. This is quite interesting because you would think that you'd fix a bug at the library level, but I think the way most software organizations works, there's a product group and there's a library group, and the product group gets reported, your application is crashing, fix this. So they fix it instead of fixing the library. The interesting part is that there's other applications using that library, and now we know of a new bug class, Yahoo. And you just grab your hard disk for another use of this, another use of this function, and get a free net meeting remote. That was fixed a few months, like, I don't know, 2 months ago or something, they fixed the net meeting remote. So they basically, when they patched the ISA server, they gave everybody the net meeting remote, and when they finally figured it out, they fixed it 2 or 3 months later. Binary diffing makes you lazy. You quit auditing because they give you bugs for free. All right. Another thing, S-channel. Now, we all remember that they published some overflow in S-channel, SSL parsing, PCT parsing, and the only information they gave is there's a bug in PCT parsing. So let's go over here, and let's diff the pre-patch MSASN1 to the post-patch MSASN1. One second. Damn it. 1 second, please. I'm getting all confused. What? Please stand by. Oh, here we go. All right, MSASN1 post-patch. And let's diff it against MSASN1. No, we're not in MSASN1, we're speaking about S-channel. I'm completely confused. Sorry for a second. All right. Was not here. Just demoed it before I went into this room, so that's the fun. Okay, S-channel. All right. So we load the new S channel, run the diff, we select the old S channel. It spawns an IDA database in the background to create all the signatures and all the graphs, and then runs through creating those fixed points. This might take a minute or two. Depending on the size of the application, it might actually take a lot longer as well. I recently diffed a Cisco image on MIPS, and it was fairly massive, but it took all night as well. So it was like an 8 or 10 megabyte executable. You're not usually dealing with 10 megabyte executables unless you're dealing with weird router ROMs. All right. Here we go. So we have a whole bunch of changes in the new S channel, so they changed more than just one thing. But they did say that the bug was in PCT parsing. So we scroll down to the only function that has PCT in its name, and have a look at it. And, well, let's look at the graphs next to each other. So this node is obviously the same as this. This is the same as this. This is the same as this. This is the same as this, but this is not the same as this. So they did something with this node here. So what's going on here? We have a loop down here, and we have some string hopping up here. And now we have the string hopping down here in the loop, but before that we have a size check for 32 bytes, for 20 hex. So what they're doing, well, what this loop here does is basically they take some string which comes from the attacker, and then they knot it and invert it and append it to itself. That's something they do in the PCT protocol for some reason. And, well, in the old version, they don't check size. In the new version, they do. Simply enough. The nice thing is you can override EIP with anything you like, including null bytes. And the total time when the patch came out to diff it and understand what the heck was going on was less than an hour. So after, like 1 hour after receiving the patch, we could start writing an exploit. And that was a lot of fun. If you're interested in this sort of topic and you want to read like a more in-depth paper describing all the stupid math behind it and stuff, there's a URL on the screen right now where you can download the paper. It's been published in the lecture notes of informatics as part of the DIMVA 2004 conference proceedings. Can I flip over to the next slide? All right. So, oh, back? All right. All right. Now that must be enough. Part 2, navigating binaries. Now, when driving a car, a frequent problem is to get from the current location to another location. We all know that problem. Now, we have a similar problem when we're dealing with, or when we're trying to trigger a certain bug or go to a certain location in a binary. We know, well, like, we have one location where we are, and then we want to get to another location. This happens, for example, if you want to reach a location where you've just been diffed and found out that they fixed a bug, or you have a static analysis tool that finds you bugs and you want to get to a certain location where you can trigger it. In both cases, the problem of finding a way from point A to point B has to be solved. Now, for some reason, when we're auditing code, use a textual representation. That's kind of like, okay, how do I get from downtown Las Vegas to Mr. Eitel's house in New York? And somebody tells you, well, okay, first you go out of the house and you take a right. And then you go for 500 yards and you take a left. And he describes it all the way from Las Vegas to New York to the specific door by describing every turn. So, and now one of those roads is blocked. What do? You need a new description and you're all confused. There's a reason why humans started inventing maps a few thousand years back. And there's no reason why we're not using maps to navigate code properly. So the general thing is, visualizing programs or having maps for programs is really important. Programs nowadays, though, are really huge, and they're not easily understood. And your brain is not built to read code. I mean, code has been around for, I don't know, perhaps let's be very, very, what do you call it? Like, let's just take a big number and say around about 100 years. Now, the human brain didn't have all that much time to evolve in that period, so we're all not optimized for reading code. We're optimizing for seeing there's a rabbit running away from us, or there's a big animal running towards us. Which means recognition tasks are significantly faster for humans to do than memorization tasks, where you read something and have to understand it. So many, many problems are not really problems, but visualization problems. And if you can visualize functional interdependencies better, it'll yield better program understanding. And if you understand the program better, you'll find more bugs. Now, I used the analogy of roadmaps before. And analogies for many things really suck, because roads and tall trees are really not the same. Like, even if you have a road crossing, you rarely ever have more than 4 roads intersecting at any point. It is quite usual to have a function calling much more or many more than just 4 functions. Road crossings, well, in general, roads are relatively sparse and they run parallel, and you don't have every road to, well, in France you do. You have every road going to anywhere in the country going through Paris. But normally you don't have, like, one place where everybody's going through, and you don't have one place where you have to go through 5 times a day in order to get to a completely different place. So we need to be careful with the analogy of a roadmap, because quite clearly programs are not quite like roads. So the first thing we would like to do at times is restructuring call graphs. The main point is that we have lots of library functions. And with a graph, we would like to visualize the interplay between the functions and which function calls which other, and what their relations is, and how they're logically dependent on each other. Now, if you have a library function like malloc, which is virtually called by every other function, then all of a sudden you're tying together logically separate parts of the graph into one big mess. And that makes things really, really ugly to look at. Now, if you remove library functions automatically, then you get a much nicer graph. First of all, library functions have a lot of edges going into them. So you just remove a lot of edges, and edges are ugly in the graph. You want to remove as many edges as possible. The other thing is that the graph layout algorithms will group connected nodes closer together than disconnected nodes. So if you're disconnecting logically disparate parts of the program, you get a much more accurate layout. So the thing is, how do you remove library functions? Now, the first idea most people will have is have a blacklist. Oh, I just remove everything that's called malloc. But the thing is, everybody will have wrappers around malloc, and everybody will build their own library functions. And we're graph people. We're not people who like string tables. So what we're going to do is we're going to remove nodes based on the characteristics on the graph. Meaning a library function will have a high in degree, will be called from many locations, and will call relatively few others. So, wait, this is on the slides, but it's changed, so. Please hold on, it's Java. All right. So what we're going to do is we're going to take a reasonably sized mail server, and this is the initial map you get. These are all the nodes and all the edges between them. Obviously, this is not too nice to look at. If you're a cat and like playing with yarn balls, that might be. But this just ain't. OK? Now, we can select nodes based on minimum or on in degree and out degree. So we're going to select nodes that have a very high in degree and just strip them from the graph. And the graph gets simpler. And we do this again. And the graph gets even simpler. Then you can relay out and actually get something that tells you something about the interrelation of these functions. You kind of have to be careful, though, because the more you remove, the more likely you're going to disconnect parts that actually belong together. So, well, just don't go nuts, even though the graph looks really nice. OK, so we have kind of started attacking the problem of getting some sort of bearings within the binary, or like getting a map of the binary. Now, a map really doesn't help you all that much when you don't know where you are on that map. So we need to find some way of putting ourselves on the map, and the simplest way of doing this is setting echo breakpoints. Echo breakpoints is a break, like you write a small debugger that sets a breakpoint on every node of the graph. And whenever it gets hit, it just sends the address of the breakpoint that just gets hit over the network and continues running the program. So you get a program trace of which function was executed at which point. This is basically the same concept I presented at Black Hat Vegas 2002. And you can visualize the results in the graph afterwards. First of all, we have to get some results. All right. Start the service. $3.80. All right, so we have a debugger now attached to the mail server. And we open up a new window because we would like to have the full graph. And we start setting a breakpoint on each and every function in this graph. And then we start talking to the mail server. Just have to find a window where I can do this. All right. And then we quit collecting all those breakpoints because there's no need to collect more than necessary. And what we can then do is we can take the functions that we hit and delete everything that we didn't hit, which gives us a layout of the functions that we actually were able to trigger. We can then play back the events in the graph to see at which point which function was called and what the order of the calling is, and so on. All right. Oh, and we have lots of different visualization modes as well. So this is information pornography. It feels kind of dirty having all these funny colors on screen, but all right. Where were we? All right. Now, well, you can do other things as well. You can use these things to, I don't know, let's take another window. Let's select an arbitrary function somewhere, like a library function that we know gets hit somewhere. What might be interesting? Blah, blah, blah. Okay, let's take SNPrintf, and please give me only those nodes that end up calling SNPrintf, and remove everything else. Oh, all right. So, well, yeah, this is great for impressing people. Okay, so what else is all this in-degree, out-degree stuff good for? Actually, library functions are not only good for cluttering up your graph, they're also interesting for another reason. Because library functions are where bugs happen, usually. Because many bugs come from the semantic issue of there being a desynchronization between what the programmer does and what the programmer thinks a function does and what it actually does. So library functions are where things go bad. The first thing is library functions give you the most punch for your money if you find a bug in them, because library functions are called from many locations, which means it's quite likely that if you have a bug in a library function, you will be able to reach that library function as well. The other thing is that most bugs have to do with somebody not properly, like not knowing all the side conditions of all the inputs for a library function. Like, I don't know, a malloc that runs up, the programmer doesn't know that if you pass in a too large value, it'll just corrupt the heap. So if you have many locations at which the library function, or at which a function is called, then obviously you'll have greater odds of one of them being screwed up. So being able to detect library function is useful on its own. So to show that this is not just pretty but useful, I would show how we used something like this in order to quickly build an exploit for the PCT bug after it was released. Okay. So let's look at the first graph. We know that the bug was in PCT1 serve handle blah 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 thing. So we look at the node that actually calls there. This node here calls PCT1 serve handle blah hello. What we do is we set breakpoints on every part of this function, collect them and color them into the graph. Now back then I didn't have the nice Java interface yet, so I had to do it all with Python scripts. God bless the TH. All right, so this was the code path that was actually taken. And now we know that if we look at this map here, we know that we took a wrong branch up here because we want to get here, 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 and we took the wrong branch here. So we zoom in. And EAX is being subtracted F8. If it's 0, it goes where we want to go. So we keep in mind F8. We add 6, we add 1, we add 1, we add 1, we add we add FFFD. And we go to the beginning of the function, or we just look at the slide. And we know that the value in arg0 member 4 at the beginning of this function, arg0 is a structure pointer, has to be 100FE. So we know that we have to set a global state variable from the structure to 100FE. And then we just search through the binary for functions setting anything to FE. And lo and behold, we find a function here. And we've colored all the nodes that do the FE stuff red. So there's 3 of them. There's one of them here, one of them here, and one of them here. So these 2 both end up in the SSL3 protocol handler where we don't want to go. There's only one which leads to PCT server protocol handler down here. So we know that instead of taking the path that was taken, which is along this path here, from this red node, we want to branch right here, and then just go through this call tree until we reach the location. And this was quite nice because after we received the patch, the time we had to spend, about an hour later we knew what the bug was. About 6 hours later we had EIP successfully overwritten. And about 12 hours later we had a fully working exploit, which was a decent turnover for rapid exploit development. All right. So enough of all this. This is not what I usually talk about. I usually talk about the big program I'm building, which never gets finished, and which I've been building for n number of years. If you've seen my Black Hat Amsterdam talk, I tried to explain some of the concepts which didn't all work, and it's one of those things where you think you're going to be done in 2 months, and then 3 years go by, and you all know the feeling, I guess. Yeah, well, so the last part of my talk will be about automatically answering the question, where does a certain value come from, or where does a certain value go to, which is really interesting for auditing code. And those questions are really hard to answer, especially if you have a language which allows you to do pointer manipulation and pointer arithmetic, and especially if you don't have any type information. Because if you have type information, you can at least infer, okay, the types are being held most of the time, and we can infer from the types where things are going. We have neither in the binary, so we have to do some stunts, which I explained in the Black Hat Amsterdam 2003 talk. I have a little bit of it implemented, actually. Let's load MSAs in 1. Oh, wait. I'll have to quit IDA and restart it. So we go into MSAs in 1. And we go to a function calling local alloc, which is the changed malloc, where they actually added the check for the overflow within the alloc. And now we'd like to answer the question, please give me a list of all the exported functions in MSAs in 1 that pass pass an input value into malloc. And then we can look at those functions and see whether they do an addition or a shift left or something similarly ridiculous. For this, we run the data flow analysis. And we wait 2 minutes for it to run because it generates about 150 megabytes of debug logs. Because I don't have a debugger to attach, so I have to debug by printf, and that just slows the execution down, having 150 megabytes of crap being written to a hard disk. So while we're waiting for the program to finish, are there any questions concerning the first 2 halves of the talk? Yes? Well, I'm building the graph based, the question is whether I'm using process tracing to build the graph. Well, I'm using IDA Pro to generate the graph, and then I'm using a network-based debugger in order to collect the events. Yeah. Well, you will eliminate some library calls, but as I mentioned before, there's wrappers around malloc and the like. So using the graph is usually a safer way of going about it, because you can have a wrapper around malloc, and then malloc will be removed, and you still have the node above it being called 250 times. So, yes, please. Which one? Yes, it is. I'm actually partnering with ImmunitySec and Black Hat to sell it. So you can look at it on the website. You know the URL for the paper beforehand? There's a website where you can look at sales material. Woohoo! And if you want to buy it, you can talk to the Black Hat folks or to the Immunity folks. And yeah. It's done. Contrary to the other plugins which I'm showing, the binary diff is actually done and working, which is a refreshing change if you're spending a lot of time with non-working programs which you're writing. So this is the data flow, this is a data flow graph of all the things going into the allocation in the end. It's not really pretty to read yet, so you just have to trust me when I tell you what we're going to do now. We're going to the very top, and if you don't recognize this assembly language, this is because it's an intermediate language which I built up one time. And we're not going to look at this node here. 1, 2, 3. Oh. 1, 2, 3, 4, 5, 6, 7, 8. 9. All right. So what we have here is we have this node which well, from the define FFFSP, you can see that this is the beginning of a function. Just trust me on this. And up here you can see that my program has determined that at this point, the value that later on gets passed into the alloc is in the input register 1. It's a simplified or a beautified version of Spark, the intermediate language. So input register 1 means the second argument to a function. Input register 0 is the first argument. So let's go to the address, 76. 2A, 4D, 2F. This thing is called ASN1 per deck table char32 string. Well, we knew that per had some weird issues. And we know that argument 4 here is corresponding to input register 0, input register 1. And then we scroll down a little bit and we see a shift left here. So they're shifting it left by 2 bits. And they're passing it into something that looks suspiciously like malloc. So we have a shift before the malloc, which might be useful if somebody gets the idea of calling this function here with a value that a user might have supplied. Such things tend to happen in ASN1. And that's pretty much already it, I guess. Any questions? The binary diff? The question is how much the binary diff costs 750 euros, which is roughly $900, single seat license. All right. And apologies for giving this half sales pitch thing. I feel kind of uncomfortable standing here. Any other questions? Yes? The question is how much overhead there is involved with doing the runtime analysis. This depends on what you're doing. You mean just setting breakpoints in every function and removing it? Well, the thing is you can automatically remove the breakpoints once they were hit. So that's quite useful for doing fast coverage analysis. Yes? The question is how much the binary changes between two compiler versions. I have no idea. Any other questions? Yes? Come again, please? If you want to do a tech analysis? Oh. Well, definitely you can patch the compiler to obfuscate code, but the experience with code obfuscation is that it's a cat and mouse game and never actually leads anywhere. So, any other questions? Then, since everybody's, oh, yeah. To be quite honest, I'm quite glad if nobody's paying attention. Any more questions? All right, then thanks. Everybody has already left. Oh.